This is Professor Gavor. We're going to talk about discrete random variables, chapter 4. And we're going to cover probably mostly the binomial distribution and Poisson geometric. We'll also look at the hypergeometric, even though I won't test you on that. You want to classify word problems by their distributions and answer questions about that. So now we're not just looking at probability randomly, but probability as some sort of formal distribution. So the first thing we have to talk about is a probability distribution function for a discrete random variable. I will often refer to this PDF, probability distribution function, as a probability density function. They're interchangeable. Associated with it is a cumulative distribution function or cumulative density function. And I will probably refer to with the word density most of the time. So not unlike our tables that we use about frequency and relative frequency, we're now assuming that the probability, the relative frequency, is a given probability. So each probability is between 0 and 1. So here's the characteristics of a probability distribution function or probability distribution. So all the probabilities are between 0 and 1 inclusive. It can be 0, it can be 1. The sum of all the probabilities is 1. And we're talking about discrete distribution. So what does discrete mean? We haven't actually defined that. Discrete, first of all, means either finite. Like if we look at this, a child psychologist is interested in a number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let x equals the number of times per week a newborn baby's crying wakes its mother after midnight. For example, the numbers are 0, 1, 2, 3, 4, 5. And we find out that this happens 2 times out of 50, 0, 11 times out of 50, 23 times out of 50, 9 times out of 50 for 3, 4 times out of 50, and 1 time out of 50. If you look at these are really supposed to have division signs. So they're really fractions. And that fractions all add up to 1. If you add the numerators, the denominators are all 50. If you add the numerators up, it becomes 13, 36, 45, and 5 is 50, so it equals 1. Now this is not unlike the frequency distribution table we used. And let me explain how this works. So let's look at this. Let's call this babies. Baby wakes mom. And let's make this bigger. So, well, let's go over here. And let's make this bigger so we can see it. And so if we have the variable x, and it goes 0, 1, 2, 3, 4, 5, and what little I know about babies, let's make these all left, right justified. Let's make them all bold. And the same thing up here. So I have frequency. And what did we have here? We had 2, 11, 23. Let me move this over a little bit so we can see the numbers. 2, 11, 23, 9, 4, 1. And just to make sure I do that right, I take equals sum and I highlight all this. Now we might normally call this relative frequency. I'm going to call it probability of x. But it's really relative frequency, and this is the PDF for this particular experiment. So I'm going to get equals 2 divided by 50, and I have to put the dollar sign between the C and the 9, so that when I copy this down, and it's all to 2 decimal places. Now I'm going to do the cumulative density function. And this difference here is that this is the probability of little x being less than, or I'm sorry, big X being less than little x. And it's not only less than, it's less than or equal to, so I'll underline it. This is the probability that big X, the random variable, equals X. So at less than or equal to waking up 0 times, there's nothing less than or equal to that. So it's just equal to 0 probability. But now this becomes 0 and the probability of 1 plus the probability of 1. So I'm going to add those 2 probabilities. I'm going to take this 0.04, the previous probability, cumulative probability, and add the current one to it. And if I add these up, when I get down to the bottom, it should be at 100%, which it is, but I have to basically make them all the same number of decimal places. Oops, I didn't mean that. So I keep making mistakes. It's this one. 2 decimal places. You should get in the habit of making these things look the same. Everything in a column should have the same number of decimal places. No decimal places, 2 and 2. Now I want to graph the PDF. So I'm going to take my X, and I'm going to hit the Command key. I'm on a Mac, and I'm going to highlight that. I'm going to say Insert, and I'm going to go to my recommended charts and do a bar chart. There we go. I'm going to probably make it look like this, where it actually shows the probabilities. And what I want to do, and let me move this over so you can see what's happening here. I want to highlight these, and I probably want to do chart design. Well, I don't want to do that. I want to do, there we go. I get this part where I want to actually reduce the gap width to 0, and I want to make the edges, the borders, I want to be a solid line, and I want them to be white, and I don't want any transparency, and maybe I want the width to be a little bit bigger. There we go. So there's my graph. And I really want the width to apply to all of these. For some reason, it only applied to one of those. I think that's better. I don't want any transparency. So there we go. There's my graph. And you can see it's skewed a little bit this way. So let's go back to this presentation. Okay, and here's one where a hospital researcher is interested in the number of times an average post-op patient will ring the nurse in a 12-hour shift. Here's 50 patients again, and the following information. We could do the same thing. I suggest you try doing what I just did in Excel. Stop the video right here, take this data set, and actually do the same thing I did. You know, graph, write the probability distribution function, the cumulative distribution function, because now you can answer all questions about it, and make a graph, a bar chart or histogram. I think that would be a good project for you to do right now. So now we ask about the mean or expected value and standard deviation of these things. So the expected value is the long-term average. What do we mean long-term average? If I toss a coin and record the result, what's the probability that it's heads or tails? We know that it's 50%, but if you flip a coin 2 times, it's a probability to tell you that these flips will result in 1 heads and 1 tail. You might toss a fair coin several times and get all heads or all tails, or majority of them heads, majority of them tails. And because each flip is independent, you don't know what it's going to be. So Carl Pearson, one of the first statisticians in history, once tossed a fair coin 24,000 times. Hopefully you had help doing it. He recorded the result of each toss obtaining heads 12,012 times. In this experiment, Pearson illustrated what was called the law of large numbers. The more I do this, the closer it gets to that theoretical probability of 50%. Even on 24,000 times. If we were to look at this, 24,000 times, what is equal to 12,012 divided by 24,000 times, the probability is 50%, 50.05%. And 1 minus that will be the probability of getting a tail based on just that experiment of $24,000. So if or 24,000 times, I get 499.5. The more I do it, the closer these numbers are going to get to 50-50. If I round it down to 2 decimal places, it does come out 50-50. If I take it to 4 decimal places, it's not. You're going to find me not using percentages as much moving forward and using decimals. If you want to talk about, you can call this 0.5005 or you can call it 50.05%. You should be able to just do that in your head by moving the decimal place over twice. Okay, let's go back here. And let's go to the next one. How do you find the expected value of a discrete distribution? And again, the second lesson in discrete distributions, there's a finite number of observations, but it can also be an infinite number of observations. But when I take, like the counting numbers, is a discrete set. 1, 2, 3, 4, 5. It's infinite because it goes up to infinity. But if I pick any 2 counting numbers, let's say 10 and 100, and I subtract the smaller from the larger, so 100 minus 10 is 90. There will always be a finite number of set elements in that, in between any 2 numbers that I pick. That makes it discrete. They're separate and distinct. There's some space between them. If you look at the rational numbers or the real numbers, like just take the numbers between 0 and 1, there's an infinite number of fractions. And if I pick 1/2 and 3/4, there's an infinite number of fractions in between there. So that's a continuous number system or continuous set. So right now we're only doing these discrete sets that are like finite numbers that only go up to n, or if they're infinite, there's space between them. So between any 2, there's only a finite number. And what we are looking at here is the mean, which we use the Greek letter mu. Remember, that's a population parameter. X bar would be from a sample. And we're not going to distinguish that much now because I think we're creating our own probability distributions, even though it's based on a sample. How do we do this? So a men's soccer team plays 0, 1, 2 days a week. Well, before we even get to that, let's just try it on our data set here. So on this baby crying thing, baby's waking up mom. Let's say I want to find the mean. So I put mean, and what do? I take equals, and maybe I should do it down here. Let me move this around. I'm going to put mean down here. Mean equals, and maybe I'll write justify it. Mean is basically this number times this number plus this number times this number plus this number times this number, and I add them all up. But luckily there's a function for that in Excel. It's called sum product. Sum product. What does that mean? It means if you click on this sum product, it gives you an explanation over here that says the sum product returns the sum of the products of corresponding ranges of arrays, blah, blah, blah. It's a little confusing, but what it does is it says if I highlight this, and then I put a comma, and then I highlight this, and it has to be an array of the same length. So these are 6 elements, these are 6 elements. I multiply these two together, and what do I get? I get 2.1. We also know that a weighted average, 2 divided by 50 is 0.04. So if I multiply 0 times 2 and 1 times 11 and add all those up and then divide the whole thing by 50, it's the same thing as 0 times 2 divided by 50, 1 times 11 divided by 50. So that formula that they showed works pretty well. So did they do standard deviation here? They did not do standard deviation, but how do you figure the standard deviation of this same thing? We just figured the mean. That was pretty easy. Well, we know that standard deviation is what? Well, let's go back to this. And I have to add probably another column here. And maybe I'll put an in between here. Well, no, I'll do it after. So I can do mu, I'm not going to use the Greek letter, minus, or x minus mu, and what I'm going to do is make that square it. Which means I'm going to raise it to the second power. So what is this? This becomes zero. Oh, I forgot to put the equal sign. Equals 0 minus this, which is the mean, which is mu. And I put parentheses around that, and I want to square it. I use the thing above the 6, which is a caret, and then a 2, that means I'm squaring it, so I get 4.41. I add all that up, and then I divide by n. I take the average of that. And what happens when I take the average of that? Average means I divide it by 5. So the average becomes this. Now I have too many decimal places. How many decimal places? Let's do it to 2 decimal places, like everything else. So it comes out to be 9.9. But that is not, that's the variance, because I didn't take the square root of it yet. The square root of it, SQRT equals SQRT, is a function that takes the square root of whatever's in the parentheses. So it becomes 3.15. That's the standard deviation. Do you get that? So now we've done mean and standard deviation. If you want to do this for the soccer problem, a men's soccer team plays 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability that they have 2 games is 0.3. Find the long-term average or expected value, or the mu, of the number of days a team plays. Well, you can do this just like I did with the other problem, but you will get these probabilities of 0.2, 0.5, 0.3, and then if I multiply the three together and add them up, what do I get? I'm going to get 1.1, so their average is 1.1, but that makes sense. The time, it's 20% chance they play 0 games, 50% chance they play 1, and a 30% chance they play 2. So I know the average is going to be between 1 and 2 and probably closer to 1. So 1.1 is not is the answer. They didn't do the standard deviation, but I showed you how to calculate that. All right, here you're playing a game of chance in which 4 cards are drawn from a standard deck of 52. You can guess the suit of each card before it's drawn. The cards are replaced in the deck on each draw. You pay $1 to play. And if you guess right suit every time, you get your money back plus $256. What's your expected profit of playing the game over the long term? So let X be the amount of money of profit that you earn. The X values are -1, and because you lose the money, and 256. The probability of guessing the answer right is, well, the first time is 1/4. The second time is independent, so it's going to be still 1/4. The third time is going to be 1/4. The fourth time is going to be 1/4. So you have a 0.0039%. So you have a 0.39% of guessing right. If you have a multiple choice test of only 4 questions, and each question has A through D, this is the same thing that we're talking about. 1/4 times 1/4 times 1/4. That's why multiple choice questions, guessing doesn't get you so far. And it's 1 out of 256. What's the probability that's the probability of winning $256? So 256 is not a random number. But the probability of losing it is 255 divided by 256. So most of the time you're going to lose the money. So how do we do this? Let's do this over here. And let's call this suit. We'll just call it the card game. So let's make this bigger so we can see it. And what do we say? Oops, I don't want to make that bigger. I want to make this bigger. Okay, so what do we have? X is, the variable is X, the random variable, and I have -1, and I have 256. Those are the only two values this can take on. So let me make these all justified. And what's the probability of X happening? Probability of big X equal to the little x. So what's the probability of X being -1? Well, we said that was equal to 255 divided by 256. And this was just the probability of this one was just 1 divided by 256. And if I add those two up, equals the sum of these two things. They should be 1. And it is. And let's make this like 3 decimal places. Okay, so the probability of winning is 0.4%, and the probability of losing is 99.6%. So if I want to calculate the mean here, and let me put the word mean right there, I'm going to do X times probability of X. I'm not doing the sum product, but I could do the sum product. So this equals minus 1 times this, and I can just pull it down 1, and that essentially is 1, but if I make these all 3 decimal places, what is this going to add up to? If I take the sum of that, I'm going to make my average gain is 0.4 cents. Well, that doesn't really make sense, does it? 0.4 cents. But if I do this over and over again, over and over and over and over again, this law of large numbers, this number here becomes what my average winnings will be. So the 256 was picked on purpose. If I make this $1,000, which makes it more enticing, now my average winnings over, if I play it 500 times, my average winnings are going to approach $2.9 on the average. Because still, I'm going to lose 255 times out of 256. So that's why they picked the number 256, to make it a small thing. Okay, so we have the card game. And here, they had the same thing. They took it to 4 decimal places. So let's take it to 4 decimal places too. We'll make it 4 decimal places. We'll make this 4 decimal places as well. And now you're making 3.9 cents. And what's the average? So the 0.23 is the average or expected win per game after playing this game over and over. I don't know if that's necessarily true, because they got 0.0023. What do we get? We got 0039. So I think we did something wrong, or they did something wrong. 9961, we have that. Oh, we made it negative. It shouldn't be negative. It should be, the probability cannot be negative. Well, no, the probability is not. And I multiply by -1, so that's what I get. I multiply by this by 256, and I get approximately $1. -9. I don't know how they did that. We got different numbers than they did. I think they did the math wrong. I would go with my numbers since I did it in Excel. I have 256 times 0.039. 256.039. And they got 0.9984. And we got 1. Because remember, the probability is 1 over 256. Of course it's going to be 1. Okay, so the binomial distribution is the next thing we're going to look at. Now, the binomial distribution is very popular. It's popular in quality management, quality control, and it's used when we talk about, what's an incoming inspection. We use the binomial distribution to determine whether we're going to accept a lot of goods by taking a smaller sample of them and seeing how many defects there are in a sample. Let's say we got 1,000 parts, and I pick 20 of them, and I measure a certain criteria, either a length or a weight or something, and if they're defective, if they're outside the range of where I want them to be, they're considered defective. So if I have I find X number in my sample, I'm going to reject the lot and either send it back to the manufacturer I got it from, or have to go through and inspect them all and sort. So if you want to look at binomial distributions on that website, that learner organization, the link doesn't work, but if you actually go to learner organization and look at binomial distribution, you'll find it. So Supposing Joe randomly guesses at a true-false statistics question. The experiment has two outcomes, and a success is guessing correctly. A failure is guessing incorrectly. So suppose Joe always guesses correctly on any statistics true-false question with a probability of 0.6. Why is it not 0.5? Because if you're guessing, it should be pure guess. But he has some knowledge of statistics. He sat in the class, he listened to the lectures, so his guess is going to be a little bit more intelligent. But he didn't study a lot, so it's not that much more intelligent than 50-50. He's going to guess correctly with 0.6% probability, and then the probability of failure is 1 minus that, the complement, and we call that Q as 0.4. This means that for every true-false question, Joe guesses his probability of success 0.6 and his probability of failure 0.4. They remain the same. This experiment is an example of what they call a binomial experiment. And this one trial is considered a Bernoulli trial, where you have two choices. You have a probability of some success being the item of the result that you want it to be, and the other choice is the result that you don't want it to be. It's 1 minus that. So P plus Q always equals 1. Q is 1 minus P. So there are a fixed number of trials. Think of the trials as repetitions. It's a true-false statistics test. It could have how many trials? Each trial would be a question. So if it's a 10-question exam, that's all true and false, he would have 10 trials. The letter N denotes the number of trials. There are only two possible outcomes, success and failure, for each trial. The letter P denotes the probability of success on one trial, and Q denotes the probability of failure on one trial, on each Bernoulli trial of this experiment. So the N trials are independent and are repeated using identical conditions. That's what defines a binomial distribution. So if you look at the binomial distribution, there's a few facts that you can look. Here's a probability density function. It's a combination of n things taken x at a time, and probability of x, the probability of the success, the item you want, is to the x power, because you're looking at how many correct did he get out of n if it's Joe taking that test. So it's going to be p to the x power, because it's going to be each trial that he got correct was p times p times p times p. And then 1 minus p, which is q, is n minus x. Now this assumes you guessed all the right ones first and all the wrong ones second. But that's why they multiply it by the combination, because they want to look at all combinations of p and q. So it really becomes n factorial divided by n minus x factorial times x factorial. Oh my God. Are you going to have to memorize this to do this problem? No, because we're going to use Excel, and there's a binomial function in Excel. The mean is n times p. The variance is the mean times q, which is 1 minus p, and the standard deviation is the square root of that. How do you know this? Memorize it. How do you memorize it in a test? Next test, you can use a formula sheet. It's that simple. So if you have a little calculus and want to go through this, you can figure out how they actually calculate the means and how they calculate the standard deviation. We're not going to bother ourselves with this because probably most of you do not have calculus, so we're going to skip that. So here's it. Here's an example. I'll do the first one. You do the second one the way I did the first one. The State Health Board is concerned about the amount of fruit available in school lunches. 48% of schools in the state offer fruit in their lunches every day. This implies that 52% do not. So the probability, if I pick a school at random, that they provide fruit is 0.48, or 48%. The probability that they do not is 1 minus that is 52. I'm interested that they serve fruit because I'm so ridiculously health conscious. So I'm going to say my probability P of success is 0.48. What would success be in this case? We just decided that. A school that offers fruit in their lunch every day. And then here's a trainer teaches a dolphin to do tricks. You answer this one. The probability that the dolphin successfully performs a trick is 35%, and the probability that the dolphin does not is 65. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. State the question mathematically. Well, that's the probability that x equals 12. Well, in both of these cases, and maybe I'll do the dolphin problem. This seems a little bit more interesting. Out of 20 attempts. So let's look at this, how I would get that answer. What's the probability of x equals 12? Well, I don't know. Let me go back to my Excel thing. So let's go to this and create another tab that we'll call Dolphin. And here's how you should set up your problems. I'm going to have n, and I can put equal or not equal, but I have 20 trials, do I not? And my probability of success is what? For the dolphin problem, I don't know. It says 35%. So I'm going to make it 0.35. Remember, I'm not using percentages anymore. They're not in the same, they are not the same number of decimal places. That's okay, because this is a probability and this is a counting number. And I may make these, I'm going to put that in yellow, which means it's something that we can change. Or maybe I'll put it in orange. Orange is the color I tend to use when I want to make an input. So then I have x. And then I have, well, let me make it down one. Let me make these bold and this way. So I'm going to have x. I'm going to have my PDF. I'm going to have my CDF, which is the probability of big X equals little x. So x equal, or this one's going to be the probability of big X, which is the random variable, being less than or equal to little x. And to make it less than or equal to, what am I going to do? I'm going to use the underline again on the less than sign. So what do we have? 0. And what do we say we wanted? How many do we want to have? You could have the dolphin performs the trick out of 20 times, 0 times, or he could do it 1 time out of 20, or he could do it all 20 times. Now, at the probability of 35%, the probability of doing it 20 times in a row is going to be very low. I imagine it's going to be 0. Now, I can go back, and here we can go back and use this, because we have a formula for combination. We learned how to use that in Excel. I know how to take 0.35 and raise it to a power, and I know how to take 1 minus p, which is q, and raise it to n minus 20 minus whatever that is, and I could do that. Yay. Or Excel is better than that. I can say it's equal to binom, and here's one that says binom.dist. That's a binomial distribution. And it says, what is my number S? Well, my number is going to be this 0, which is in this case B7. I put a comma on it. It says, how many trials are we doing? And it's 20 trials, and I want to put a $sign there, because when I drag it down, that's not going to change. What's my probability? Well, my probability of the success, the dolphin doing the trick properly, is C3. And again, I want to put a $sign, because that's not going to change through the whole problem. And then it says, Am I doing a cumulative distribution? I could put either the word true if I want cumulative distribution, but I want probability. Look at, they use mass function, probability distribution function, probability density function. Those are all simultaneously. True is 1, false is 0, so I only have to put a 0 there. And then I get this probability, and I can copy it all the way down here. And if you see, it all adds up to a sum of 1, which is right. But look at it, I got scientific notation and stuff. How many decimal places do we want to take this to? 3. The probability of doing 0 times is 0 to 3 decimal places. If I do it to 4 decimal places, it's a fraction. It's 0.02%. So let's 3 decimal places enough. Probability of doing it 5 times is 1/27. Now, if I want to do the cumulative density, I can do my old trick of making this equal to that, and then adding, I could do this, right? I could say equals the one above, and the probability density function at that x, and then I can just take it all the way down, and it, right, by the time I get to 14, it's 100% probability that it's 14 times or less, it would be 1, so at 3 decimal places. Or I can go here and I can copy this over. It's going to give me a weird number, but because I don't have, I got to move, oops, sorry about that. I don't want to enter all this stuff. I just move this one back here, and I move this one back here, and I change the 0 to a 1. And then if I copy this all the way down, it's 0 everywhere. Why is, oh, I know what happened. It became C7. I got to move this one over too. So I can just move them over. Now let's see if it works out right. I think it does. It looks like it did before. Now if I want to graph this, insert, recommended chart. I want a chart that looks like this. Now it's a different shape. I'm not going to put the numbers in there because it's not going to read very well, but I'm going to I am going to go through here, and I'm going to reduce the gap width to 0. I'm going to go here and put a solid line with a white border, and therefore there's my probability density function. Now, once I've done this, here's the cool part. And let's say I want to do other things. What if I want to do mean, variance, and standard deviation? What does it mean? It's n times p equals this times this. So the mean is going to be 7. Because it really is saying you're taking 35% of 20. Well, 35%, 30% of 21 is 7, because 3 times 7 is 21. So 35% of 20 is probably 7. That's probably a good thing. So now if I want to get the variance, I take the mean times parentheses 1 minus p. I never have to really worry about what q is, because q is always 1 minus p. That's the variance. Again, I don't have to worry about, if I want to have the same decimal place, I can. I might do that then. And then if I want the standard deviation, it's the square root of this. Boom. And so let's make them all 2 decimal places. Now, if I go here and I change my probability, let's change it to 50-50. Watch what happens to the graph. It becomes symmetrical. And the mean becomes 10. Because I'm doing 50 cents. This is a the probability of flipping a coin 20 times and getting heads or tails. Now let's say I make it, what do we have before, 35? Let's say I make it Q, which is 65. Now Q and P, I've switched what they are. Well, I get the same graph, except it becomes a mirror image of itself. It's skewed towards the top. So if, let's say I make it only 0.1. It's not the smartest dolphin in the world. I make it a 0.1 probability of the thing ever doing a test. Well, because it's such a low probability, he's most of the time going to do it 0 times, because he only has a 1% chance of getting it right. And on 20%, on 20 things, a 1% chance of 20 is less than 1. But you do get the occasional 1, you get the occasional 2, but then it goes to 0 very quickly. What if it's a real smart dolphin and he can do it 90% of the time? Well, it's skewed the other way, where it means that he can do it 20%, but now the mean becomes 18. You can see the mean and the mode are kind of the same, and this is not always the case. And I get 1.8 and 1.34. So if we go back to the original, once you do something like this, you can analyze the questions. So 0.35. Let's go back to the original question. And it says, what's the probability that you could do it 12 times? And it would be 1.4% or 0.014. What's the probability that he could do it less than six or less times? 41.7%. What's the probability they could do it more than 6 times? Well, it would be 41. It would be the complement of this. It would be 1 minus 0.417. What's the probability that he could do it between 3 and 5 times? Well, I highlight the PDF 3 to 5, and I go down here, and it says the sum of that is 0.233. So you can answer every question by calculating the entire PDF and CDF table of this. And you should get used to doing that. So what happened? We did that. So you try it on the state health board with the school things, or you do it on this coin flipped 15 times. It's the same problem I did, except instead of 15, we did it 20 times. And here the P is 0.5, and the Q is 1 minus that is 0.5. But if I wanted to switch that, well, let's see what happens if I switch it to that. 0.5, and let's say I made it 15. Well, here, it immediately gives me, I don't count the things where it has this error statement, because it's giving me, saying we can't calculate that number. And really, we only want to look at this part. And the graph reflects that. But if I make it 20 times with the coin, it will go back. So if I put an if statement, if it's infinite or not calculable, I could leave it blank. And I have basically a calculator that can do n up to 20 and for any p. And I have my binomial distribution calculator here. And it will switch the mean and standard and variance. So let's change this to 0.15 and see what happens to the mean. It changes to 7.5. It changes the variance and standard deviation. Let's change it back to 20. And let's change it to the dolphin problem, which is 0.35. And there you go. So what else do we have here? It's been stated that 40% of adult workers have a high school diploma and do not pursue any further education. If 20 adult workers are randomly selected, find the probability that at most 12 have a high school diploma but do not pursue any further education. How many adult workers do you expect to have a high school diploma but do not pursue any further education? So X is the number of workers who have a high school diploma but do not pursue any further education. And that is, the probability of each one is 0.41. So we have 20 workers, and so my N is 20, My P is 0.41. My Q is 1 minus that, which is 0.59. It's a binomial distribution. This uses little tilde to say X is distributed B binomial with 20 trials and P. N being the number of trials, P being the probability. So find X less than 12 and X less than 20. Less than 12. So if I go here back to my dolphin problem, I could probably do this. They got 0.9738. So what do we say? There's 12. And we do 41%, 0.41. And we want to find the probability of, well, we had 20 students, I'm sorry. So we're using the full 20, which is good. What's the probability of it being less than 12? And if I make that bigger, 0.9738, what is it? 0.9738. I'm lazy. I don't want to do the same calculation all the time. Why don't I just have a calculator that just gives me all the probabilities, and now I can answer any question just by changing these two numbers. Is this cheating? No, it's being smart. That being said, okay, so we're not going to do the calculator, but if you want to look at it and use your TI calculator, you can calculate these things. You put binom CDF, because you're looking for a CDF less than or equal to 12, 20.04, and it's not showing the 12 in there, but you would write the 12 as well. That's why I don't like the calculator, because I've got to hit this arrow to see what else is there. So we're not using the calculator. So here's the binomial 20.41. What does ours look like? Gee whiz, it looks pretty close to the same thing. And what's the standard deviation? 2.2. What do we get? 2.2. So let's make this a calculated, if we want, we can put that in yellow, because that is something that comes out. And we could put that in a box. I could put all this in a box if I want. And I can format this so that if I make it less than 20, it makes the things that don't count blank. So if you want to try other problems, try these problems. Create the whole, in Excel, go in there, use a binomial distribution, and answer these questions. 32% of the students participate in a community volunteer program. If 30 students are selected at random, well, we only go up to 20, so I have to change it to 30, but I could extend that. I could copy paste it into another one and make it 30. X being less than 14, less than or equal to 14 is 96.95 or 97%. Here's another one. It's Jerry's Art Supply Catalog. 8 of the pages feature signature artists. Suppose we randomly sample 100 pages. Let X equal the number of pages that feature signature artists. What value does it take on? So you have up to 8. You're taking 100 pages of the catalog. The probability is 8 divided by 560. So you'd want to calculate what that is. Now you could do all these calculations, or you could just create the whole table and answer any questions. So let me cover the geometric distribution next. The geometric, and one thing we should do too is I meant to talk about dice. We never talked about the very simple problem of dice, which we did in the, if I have dice, and let's call this one die, or let's call this the dice problem. So we're going to have two problems. One die, and let's make it bigger. And so what do we have for X? X is 1, 2, 3, 4, 5, 6. Is it not? So let's make this left justified. Or right justified, make it bold. And what's the probability of X happening? Well, if it's a fair die, everything is going to be equal to 1 divided by 6. It never changes. I expect each one to be equally likely. I have one, there's only one way of rolling a 1 out of 6 possibilities. There's only one way of rolling a 2. And if I add all these up, what do I get? I should get 1 out of it. Sum of 1, 6, 6, 1, 6 should be 1. And it is. So how many decimal places do we want to take this to? Let's take it to, and I'm not even going to do the PDF here. This is the probability density function. Well, let's leave it at that. So if I graph these, and I put insert recommended chart, gee, it's not real exciting, is it? If I click on this, what do I get? I get, let's change the gap. Let's go over here. Put a solid line in there. Let's make it white. And that's that. And if I make it that way, it puts my probabilities there. Sorry, by doing that, I still have to then go back and get rid of the gap. And I got to go back and put my solid line, make it white. Well, okay, so there's my probability density function. What's the mean? They're all equally likely. What's the mean of this going to be? What's the mean? And I'm going to use the sum product again. I'm not going to do all that calculation. The mean is going to be equal to the sum product of what? 1 through 6. And all this added up together. All these, multiply each one by 1/6. So I add up all those numbers and divide by 6. Well, what's going to be the average of this, of 6 numbers where they're all equally likely? It's going to be between the 3 and 4. It's going to be 3.5. Yay. This is called the uniform distribution, where every discrete element has an equal probability of occurring. So this is one die. Let's make that bold. Let's make it that color. Let's go and do 2 die now. A pair. Dice. Well, what do we have here? How does this work? Let's move this over a little bit. Well, I have die number 2, and I have well, let's make it this way. This is die number 1. And what do I have? I have, again, 1, 2, 3, 4, 5, 6. And then if I have, let's make that color. Let's make it bold. And then I have, let's call this die 2. And I have, what do I have? Maybe I'll do it this way. Well, I have 1, 2, 3, 4, 5, 6. And let's do that so we can see it nice and easy. And let's make all this bold. And let's make these bold. And let's make them all light blue. Okay. Well, what's the minimum I can roll? I can add this plus this, and I get 2. And if I move it all the way across, so I get a 2 and a 1, I get a 4. If I get a 1 and a 6, now why did it do that? Oh, I know, because it's not, silly me, sorry, I should probably do it. I probably have to make this fixed. I have to make this, I have to put the $sign before the H. So I get 2, and if I bring it across, it should work. I add 2 and 1 is 3 and all that. So if I roll them down this way, what do I get? That doesn't really work. 2 plus 1 should be 3. Oh, I've got to make this. I got to make the $sign here. Let's see if that works. Yep, that works. 6 and 6 is 12. 5 and 4 is 9. But let's look at here. I have one way of getting a 2. I have one way of getting a 12. Is there any other 12s or 2s on there? No. But I have 2 ways of getting what? A 3. There's 2 ways of getting an 11. There's 3 ways of getting a 4. There are 3 ways of getting a 10. And so forth. There's 1, 2, 3, 4 ways of getting a 5. There are 1, 2, 3, 4 ways of getting a 9. And there are 1, 2, 3, 4, 5 ways of getting a 6. And 1, 2, 3, 4, 5 ways of getting an 8. And 1, 2, 3, 4, 5, 6 ways of getting a 7. Well, when I roll 2 dice, it complicates it so much. So how does this go? If I want to do this now, I have X for 2 dice. I don't want it there. I want it right here. X. And I have, it goes from 2, and I add to each one, I add 1. So I can get a 3, and it goes all the way to where? 12? Let's stop at 12. There's 36, 6 times 6, there's 36 ways this happens. There's 36 possibilities. So I'm going to get my probability, my frequency is going to be 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. What did I do wrong? I'm going to get, I did it wrong. 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. Is that right? I can roll a 12 frequency of once for 2, and as I go up, 2 3s, 3 4s, 4 5s, 5 6, 6 7s, and then it starts going down again. So what is the sum of this? It should be right there, 36. So if I want to do my probability of X occurring, of getting a 2, it should be equal to 1 divided by 36. Remember, I want to keep that 36 fixed, so I put a $sign there, and I copy this all the way down. And I don't want all those decimal places, so let's take it down to 3. And now let's draw a picture of this X and this, this X and this probability. So that's my 2 dice now. And it's not uniform anymore. And if I go here and I say, insert, recommended chart, and I do this, oh my God, I get like a bell-shaped kind of curve here instead. So if I click on the bars and I reduce the gap width, and maybe I'll click on that one where I get the probabilities. Now I reduce the gap width. I go here and I'd make it a solid line, and maybe in this case I make it red instead of white borders. And look at this. Here's the difference between the two. Very interesting. 1 dice is a uniform distribution. 2 dice becomes almost a bell-shaped curve. The average is going to be what? I'm pretty sure it's going to be 7. So how would I figure that out? I would do it again. Mean equals, and I would say equals sum product of what? That times that, and darn if it isn't 7. Okay, so I'm going to end this video now, and we'll call this part 1. We'll have a part 2 for this chapter where we look at the geometric, Poisson, and hypergeometric distributions only. So hopefully it will be a little bit shorter, but it's the same kind of thing that we've just done. Thank you for paying attention, and we'll look at the geometric experiment starting in part 2. Thank you so much.